We now discuss the solution of a problem from the section Real Analysis, and the question is related to the limit superior and the limit inferior of the given four sequences. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and this question is from the section C. The given question is, which of the given sequences, sequence AN, satisfy the following identity? Limit superior of AN as n tends to infinity is equal to minus limit inferior of AN as n tends to infinity. We are given four options. Option 1, AN is equal to 1 by n for all n. Option 2, AN is equal to minus 1 to the power of n multiplied by, in brackets, 1 plus 1 by n for all n. Option 3, AN is equal to 1 plus minus 1 to the power of n by n for all n. Option 4, the sequence AN is an enumeration of all rational numbers in the open interval minus 1 to plus 1. So, we are given four sequences in these options, and we have to decide which of these four sequences satisfy the identity limit superior AN is equal to minus limit inferior AN. We now discuss the solution of the problem in detail. Let's first of all take the sequence that is given in option 1, that is AN is equal to 1 by n for all n belongs to n. Now, limit n tends to infinity of AN is limit n tends to 1 by n. It is very well known. It is equal to 0. So, this will tell you the sequence AN converges to 0. The sequence AN converges to 0. When a sequence converges, then both the limit superior and limit inferior exist, and they are equal, and they are equal to the point of convergence of the sequence AN. So here the sequence AN converges to 0. Therefore, limit superior is equal to limit inferior is equal to limit of the sequence that is equal to 0. So that is the one. So the limit superior is 0, limit inferior is 0. Therefore, limit superior of AN is equal to minus limit inferior of AN is satisfied because both are 0. So thus this identity limit superior of AN is equal to minus limit inferior of AN is satisfied. Therefore, the sequence AN that is given in the option 1 satisfies this identity. We move to the second sequence. The second sequence is, the nth term is given as AN is equal to minus 1 to the power of n into 1 plus 1 by n for all n belongs to n. Now, let us write down the terms. A1, put n is equal to 1 in this, it will be minus 2. A2, n is equal to 2, minus 1 to the power of square is plus 1, 1 plus 1 by 2. A3 will be negative 1 plus 1 by 3. A4 will be positive 1 plus 1 by 4. A5 will be negative 1 plus 1 by 5. A6 plus is equal to 1 plus 1 by 6. A7 is equal to minus 1 plus 1 by 7. These are the terms, etc. etc. Now let's write down the range. Let's first of all see modulus of AN is modulus of minus 1 to the power of n into 1 plus 1 by n. Mod of minus 1 to the power of n is plus 1. So it will be mod of 1 plus 1 by n. And this is less than or equal to 2. Less than or equal to 2 for all n belongs to n. Right. That means there exists a positive m greater than 0 such that mod of an is less than or equal to m for all n belongs to n. So this tells you the sequence an is bounded. Now we recall Bolzano-Weierstrass theorem, and the theorem says that it has a limit point. So now by Bolzano-Weierstrass theorem, this sequence has a limit point, at least one limit point it has. Now our search is how many limit points are there for this sequence. Who are they? We want to find all the limit points of the sequence an. Agreed. We continue. So those are the terms of the sequence. Agreed. Now write down R. Script R is the range of the sequence an. The range means what? The range means the set of all the terms. So the set of all the terms we have written A1, A2, A3, A7, etc. we have written. Now in this I will separate the negative terms and write. So I will separate the negative terms. This is the red ones what we have is the negative terms. The positive terms are in black color. 1 plus 1 by 2 plus 1 plus 1 by 4, comma 1 plus 1 by 6 and so on and so forth. Now look at these negative ones. These negative ones. Now we observe that minus 1 doesn't belong to the range of the sequence. But however, every neighborhood of minus 1 will contain infinitely many points of these red ones. That means every neighborhood of minus 1 contains infinitely many points of the range. Therefore, minus 1 is a limit point of R. In a similar fashion, 1 is also a limit point. Every neighborhood of 1 contains infinitely many points of R. Therefore, 1 is also a limit point. Observe that every neighborhood of minus 1 and 1 contains infinitely many points of R. So this tells you minus 1 and plus 1 are the limit points of the range of the sequence. Further, there are no other limit points. You can check. There are no other limit points. Agreed. So thus R prime denotes the set of all limit points of R. That is precisely the set of all limit points of the sequence. There are just two elements only, that is the set consisting of minus 1 and plus 1. Now we recall, when we have the set of all limit points of R, the limit inferior of an will be the smallest limit point of the sequence. Who is the smallest limit point? Minus 1. Limit superior of an is equal to the largest limit point of the sequence an, that is 1. So limit superior is 1, limit inferior is minus 1. So limit superior of an is equal to minus times limit inferior of an. Superior is 1 minus times minus 1 plus 1. So thus the identity is satisfied for this sequence. Thus the sequence an given in option 2 satisfies the identity. Agreed. We move to the next one. Now option 3, an is equal to 1 plus minus 1 to the power of n by n for all n. Note that this sequence an has two subsequences, a to n, that is even indexed terms. A to n is equal to 1 plus 1 by 2n, because minus 1 to the power of 2n is positive. And odd indexed ones, a 2n minus 1 will be 1 minus 1 by 2n minus 1. Now observe this. A to n, the sequence a to n, that is limit n tends to infinity of 1 plus 1 by 2n is 1 only. Limit n tends to infinity of a to n minus 1 is again 1 only. 1 only. So therefore, these two subsequences converge. These two subsequences converge to 1 only. This also converges to 1. This also converges to 1. So both the subsequences converges to 1. And we have a theorem in real analysis. If the odd indexed terms, the sequence of odd indexed terms, and the subsequence of even indexed terms, they both converge to the same limit L, then the originals, the given sequence also converges to L. So this will give you the sequence AN converges to 1. That is, limit n tends to infinity of AN is equal to 1. Now the limit exists, therefore limit superior, limit inferior exists, and they are equal to limit of that limit. So limit superior is equal to limit inferior is equal to limit that is equal to 1. Now what about the identity? Limit superior of AN is 1 minus limit inferior of AN is minus 1. 1 is equal to minus 1 is not possible. Therefore, they are not equal. But the limit superior of AN is not equal to minus limit inferior of AN. So, the sequence AN given in option 3 does not satisfy the identity. Let's move to option 4. Option 4 will be interesting one. In option 4, the sequence AN is an enumeration of all rational numbers in the open interval -1 to +1. Agreed. Now, first note that the set of all rational numbers that are present in the open interval -1 to +1 is given by the open interval -1 to +1 intersection Q. And it is a countable set. Why it is countable? We know Q, the set of rational numbers, is countable. Now -1 to +1 open interval intersection Q. There are infinitely many rational numbers in this, and this is a subset of Q. And what kind of a set it is? It is an infinite set. -1 to +1 open interval intersection Q is an infinite subset of Q where Q is countable. That means, and we know that every infinite subset of a countable set is countable. Therefore, the open interval -1 to +1 intersection Q is countable. Agreed. So these, the rational numbers that are present in -1 to +1 are countable. Therefore, the elements of -1 to +1 intersection Q can be indexed as Q suffix n, where n belongs to n. Because it is countable, you can set up a mapping. Therefore, they can be indexed as Qn, n belongs to n. Now, let An is equal to Qn, n belongs to n. Thus, we got a sequence An which is an enumeration of all rational numbers in the open interval -1 to +1. Now, for this AN, this sequence AN, what is limit superior and limit inferior? Let R be the range of this sequence AN. That means range means the set of all the terms, that is AN, n belongs to n. Notice that every real number R belongs to the open interval -1 to +1 is a limit point of R. Why? Because one reason, first is the rational numbers are dense and every neighborhood of R contains an infinite number of points of R. You take every real number, small r belongs to the open interval -1 to +1 is a limit point of R. How? Because every neighborhood of R contains infinite number of points of R. Why infinite number of points of R? Because the rational numbers are dense in -1 to +1 intersection Q. That's why every real number or that belongs to open interval minus 1 to plus 1 is a limit point of R. Further, 1 is also a limit point. 1 is also a limit point because every neighborhood of 1, some portion, that is the half of the portion to the left, will lie in minus 1 to plus 1 intersection Q. That is in R. Therefore, how many are these? These are infinitely many. Therefore, 1 is also a limit point. Similarly, minus 1 is also a limit point. So, now R prime, the set of all limit points will be all real numbers that lie in between open interval minus 1 to plus 1 union the endpoints 1 and minus 1. That means the closed and bound interval minus 1 to plus 1. So further, minus 1 and 1 are also limit points of R. Thus R prime, the set of limit points of R, that is precisely the set of all limit points of the sequence AN, is equal to the closed and bound interval minus 1 to plus 1. Agreed. So now we have found all the limit points of the sequence. Now, limit inferior of AN will be the smallest of all the limit points. Smallest limit point of the sequence. So all limit points we know. And this is closed and bound interval minus 1 to plus 1. The smallest limit point is minus 1. And the limit superior is equal to the largest limit point of the sequence AN. That is the largest limit point in this is plus 1. So thus limit inferior of AN is minus 1, limit superior of AN is equal to 1, and it satisfies the identity. What's the identity? Limit superior is equal to minus times limit inferior of AN. So thus this enumeration, that the sequence AN, which is an enumeration of all rational numbers in the open interval minus 1 to plus 1, also satisfies the identity. So the sequence AN given in option 4 satisfies the identity. Agreed. And our question is what? We have to find out all the sequences which satisfy that given identity. So in our discussion we have seen option 1, option 2, option 4 satisfies the identity, option 3 does not satisfy. So therefore, the answer to this question is option 1, option 2 and option 4. That is the detailed discussion of the solution of the problem from the section real analysis, and the problem is related to the limit superior and limit inferior of the given 4 sequences. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.